Okay, so what I want to do right now is talk about convection. And in particular, I want to talk about the Rayleigh number, which is a number that gives you an idea of what the convective vigor of a system might be. And so we're going to derive the Rayleigh number. And the sort of system we're first going to start with is a one-layer system here, where the bottom is hot and the top is cold. This might be for the entire mantle of the Earth at 3,000 kilometers depth, where it's 2,000 degrees or so, and at the surface, it's effectively 0 degrees Celsius, and the thickness of this layer is about 3,000 kilometers. Because it's hot at the bottom and cold at the top, what actually happens is that when you have something hot, your material actually expands at an extent that's controlled by the thermal expansion coefficient. And if it expands, it becomes lower density, and if it becomes lower density in a gravitational field, it has a positive buoyancy. And as a consequence, it'll rise to the surface, which is hot, okay? And that's an upwelling. But as it reaches the surface, and impinges against the cold interface at the top, that's the atmosphere, and moves to the side, it loses its heat vertically towards the surface and it cools off, therefore thermally contracting or densifying and then coming back down. And so this is essentially how you generate a convection cell. You have upwelling and you have downwelling cells. So what we'd like to know is under what conditions does a system where it's hot deep down and cold at the top actually start to lose heat by thermal buoyancy driven advection, meaning the material actually moves, advects, moves upwards, instead of just sits still and loses heat by thermal conduction. So we'll talk about thermal conduction later on. So in my previous lecture, we looked at the Stokes settling velocity, and the way we're going to do this is to consider a blob like this of radius r here, and it has a density contrast relative to its surroundings, okay? That is controlled by how hot it is. Let's say it's a hot blob, so density contrast is equal to some reference density times alpha times delta T. Okay. Alpha is the thermal expansion coefficient. Delta T is the temperature. This would be temperature at the bottom, temperature at the surface, and delta T is equal to TB minus T0. In this case, down here, delta T is the temperature of my blob with respect to the temperature of the surroundings. So it's hot, and if it's hot, it wants to rise at some velocity, okay? And we previously showed that the rise velocity is going to be on the order of delta rho g r squared over eta. Eta is the viscosity of the surrounding fluid. That's what's actually deforming. The viscosity of the blob doesn't matter as much, so long as the viscosity of the outside of the fluid is higher. And remember, with this Stokes settling or Stokes rising velocity, one of the most important things is the size of this blob, and it goes by the r squared. So the bigger you are, the faster you're going to go, all other things being equal. And now what we're doing is we're saying that this density contrast is not a compositional contrast, but a thermal contrast. So this is a thermal buoyancy. So I only need to plug in my density difference here as a function of temperature here, and then what you get is rho 0 alpha delta T G r squared over eta, okay? So let's look at this. Obviously, if it's big, it rises fast, so r squared. But if the temperature difference is very large, there's a large thermal buoyancy, and the density is very high. Density difference is very high, so it rises very fast. And of course, viscosity has a moderating role. If it's too high, and it causes the viscosity to go down. Now, to understand whether this blob is going to rise, we have to think about time scales. Here's a hot blob, and as it rises upwards, it's going into colder material, so it's going to lose its heat. And if it cools off, then the delta T gets smaller, and therefore it loses its thermal buoyancy, and it'll stop rising. So you sort of get the idea. So we're interested in two sorts of time scales. One is the time scale it takes to cool off and knock out this thermal buoyancy, and the other one is how long it takes for it to rise. And the one that wins will tell you a lot about how the system behaves. So the time scale for cooling is the diffusive time scale here. That is, we're going to assume that heat is going to diffuse by conduction out of the body, the sphere, into its surroundings. And the other way is to advect the heat up. And so which one's faster, advection or conduction? So let's look at the conductive time scale, and that's going to scale as r squared over this thermal diffusivity. Thermal diffusivity is meters squared per second, and that's a material property and a measure of the efficiency of heat is diffused through your medium, and of course this goes by r squared. Now the time to rise advectively, like to flow upwards or float upwards, I should say, is then just, you can think about the characteristic time scale that would be r over the velocity, right? R has units of meters, velocity is meters per second. So the end result is that you have seconds there. And so if the body can move a distance r, basically the length scale of itself, then we consider it moving. Okay. Now we can look at this ratio, T of cooling by conduction divided by the temperature of rise, which is advection, as a competition here. And that would be taking these two and combining them, r squared over kappa. And this u, or this velocity, is what I just laid out there. And that ends up being rho 0 alpha delta t g r squared eta over r. It's a horrible eta, sorry about that. Nice kind of combined terms, and what I'll get you here is rho alpha g delta t r to the 3 cubed divided by kappa over eta. Okay. So you can envision that if the time for cooling is very short, then this thing is going to cool off very quickly and lose its buoyancy, and it can't rise. The system is not going to convect. On the other hand, if it takes a long time to cool off your body, then advection is going to win, and the system is going to convect. And that's this ratio here, Tc over T rise. And this ratio is basically called the Rayleigh number. Okay? And so when it's high, you can think of this thing as convecting vigorously, and when it's low, it doesn't convect vigorously. And it scales. It's important to look at these variables there. Obviously, if the delta T, if the temperature contrast is 0, then there is no thermal buoyancy. And as a consequence, this quantity is 0, and you can't convect. Another important factor is R, because it goes by the cubed. So if I were to apply this, we can take this and transfer it to the layer system. Well, I'm going to take my radius, my spherical blob, to be the layer thickness, R. Well, because it goes by the cubed, if I have a very thin layer, say like a basaltic sill, magmatic sill, it might not convect because the Rayleigh number is low. On the other hand, if I have a very large or very thick layer, very quickly it will start to convect. The things that will go against convection or make it less efficient are the guys also in the denominator. Eta, right here, which is the viscosity. Obviously, if the viscosity is very high, and it's going to be more sluggish, so you can envision waters in a pan on your stove, heated from below, compared to, say, syrup heated from below, well, the water will convect more vigorously because the viscosity is low. It's on the denominator here. Thermal diffusivity matters a lot. That doesn't change so much, but obviously, if thermal diffusivity is very high, then you cool off very quickly and you can't convect. Okay, so low thermal diffusivity would favor convection. Now, the most important quantities are, of course, delta T and obviously R, because that goes by the cubed. And the other one, of course, is eta. And for when we're thinking about Earth science-related problems, eta, although there's no power to it, effective temperature, which we really didn't take into account here, but also which we would have to later on. But eta depends very strongly on temperature and also depends on composition. So orders of magnitude, I can say, for example, a basalt has a viscosity of 1 pascal second or so, maybe less. A rhyolite or granitic type of magma is 10 to the 6 pascal second, so 1,000,000 times higher. Viscosity of the mantle, solid mantle, might be 10 to the 21 pascal second. So material property variability plays a huge role in controlling this Rayleigh number. Now, one of the things we can ask is, does Earth's mantle convect, right? Okay. The thing we want to know actually is that the Rayleigh number, it turns out, for things to convect, has to be greater than some critical Rayleigh number. Okay, although I have this ratio and it looks like if it's greater than 1, you would say it convects. It's not as simple as that. You have to go through some linear perturbation analysis to figure out what this critical Rayleigh number might be. And it turns out it's about on the order of 10 to the 3. It's something I can't derive for you here. You'll have to take my word for it. So as long as the Rayleigh number is greater than about 1,000, this thing is going to start to convect. The bigger it is, of course, the more vigorous that sort of convection is going to be. So let's put some numbers in for the Earth's Rayleigh number. So here we go. That's the density would be about 3 times 10 to the 3 kilograms per meter cubed, right? The thermal expansion coefficient is about 3 times 10 to the negative 5 per Kelvin. Okay. Gravity is about 10 meters per second squared. Delta T, let's think about whole mantle convection. The surface effectively, let's just say 0. And the base of the mantle, core mantle boundary there, 2 to 3,000 degrees, right? Since I'm looking only order of magnitude, I'm just going to put 2 times 10 to the 3 here, Kelvin. Obviously, maybe I should put 3, but it doesn't really matter. And then R, where we're talking about, is 3,000 kilometers from the top of the Earth to the core mantle boundary. So that's 3 times 10 to the 6 meters, right? I'm going to convert kilometers to meters, and there's a cube right in here. Note, I am putting everything in units of SI, so everything is consistent. And then you're going to divide by thermal diffusivity and viscosity. The thermal diffusivity is about 10 to the negative 6 meters squared per second. And viscosity might be about 10 to the 21 pascal seconds. Okay. Again, all this in SI units, so I can do it, can just go ahead and calculate accordingly. So what you get here for the Rayleigh number of the Earth, or the mantle, is about 10, what did I get here? About 10 to the 8 or 10 to the 7, okay? depending on what viscosity you use in some of these material properties. Either way, this is much, much greater than 10 to the 3. So today, the Earth's mantle is convecting vigorously. Okay, now there is some interesting implications of this equation, the Rayleigh number. Let me write it again here. Rho 0 alpha G delta T R cubed kappa eta. If you were to go to a different planet, which is smaller or bigger, then the gravity will be different, G. A small planet would have a low G, so all other things being equal, convection might be a little bit more sluggish. Big planet, you might not even need a very large radius, for the layer, sorry, not the radius, the layer thickness. If gravity is high, you would have more vigorous convection. Viscosity, as I said, plays an important role. If you were to think about yourself on an icy planet where you're not thinking about silicate rocks controlling viscosity, but say more like water or hydrocarbons, eta can be quite low and you could get convection much earlier on. The other one is thermal diffusivity. That could change, actually, it's dependent on temperature and pressure. It can be modulate the Rayleigh number. And finally, the one is thermal expansion that we often forget about. We always assume it's constant. Not only does that depend on temperature, but also pressure. It's the phenomenon of the anharmonic side of the oscillations of the atoms as they're connected to each other by a bond. And as you increase the pressure to extreme pressures, like at the core mantle boundary, you become more harmonic, and so the thermal expansion coefficient starts to get smaller and smaller and smaller. And when thermal expansion, when you don't have that, it doesn't matter what your delta T is, you cannot have thermal buoyancy. As a consequence, you cannot have upwellings or plumes for that matter. Okay, and I think that's it for now.